So let's talk about dimensional analysis. In physics, you are going to do lots of rearrangement of very large equations. You will do substitution into equations and then rearrange them. You will solve 3 different equations for 2 different variables and then shove them all together. It's lots of fun. When you do that, there's a whole lot of potential to make stupid algebraic mistakes. Ask me, I've made them all. So one of the tools that we use, and these last 2 things that we're going to talk about are basically tools that we use to avoid screwing up. That could be the heading of these last 2 little learning goals. Dimensional analysis is a very useful tool. And you guys are not, when I used to teach physical science to freshmen or sophomores, there were a lot of kids, and this was general physical science, who struggled with rearranging 3-part equations. And even when I get academic kids in chemistry at the beginning of the year sometimes, they struggle. And I can, after enough years of teaching it, I can tell you what the most common mistakes are in those kind of rearrangements. And here we've upped the game significantly. The equations are much bigger, the rearrangements are much more interesting, much more complicated. So how do you check yourself to make sure you didn't screw it up? I'm really big on making sure you didn't screw it up. You do dimensional analysis, and that is just looking at the units in a problem to see if they check out. If they check out, then we can say, okay, the equation is reasonable. Now, it doesn't prove that it's correct. It's just one of the check boxes that you can say, okay, well, the dimensional analysis is okay. You did this in chemistry with molar conversions, where you check to make sure, and with the conversions you just did in here, where you check to make sure all your units and your chemicals cancel. That's a form of dimensional analysis. Now, I'm going to introduce you to a cartoon that I dearly love. This is XKCD. I would highly advise you to go check them out. They publish a new cartoon every Monday, Wednesday, Friday. My hobby, using dimensional analysis. Planck energy divided by pressure at the Earth's core times EPA combined gas mileage of the Prius divided by minimum width of the English Channel equals pi. It's correct to within experimental error and the units check out. Must be a fundamental law. But what if they build a better Prius? Then England will drift out to sea. I'm going to start off with this, and this is one of the first equations that we'll start to use in here. Velocity is equal to displacement over time, often shown as v equals delta x over delta t. This was the form that you probably used in physical science. We're done with that. So we've got velocity equals delta x over delta t. And let's say that we're solving this for delta t. Well, actually, first let's solve for delta x. That's easy. So we have to solve this for delta x. We want to know how far we travel in a certain interval of time at a certain rate of speed. So we have this. To check our algebra, and the algebra is right on this. You all know it. You can all see it. It's very easy. We do dimensional analysis. When we do dimensional analysis, we start off by plugging in the units which each variable would be using into the equation. So velocity, in this case, and it could be in a lot of different units. It could be in kilometers per hour. We're going to say it's in meters per second. That's the one we use most commonly here. Time is in seconds. And displacement is commonly in meters. So we're saying that meters per second times seconds equals meters. Well, if we actually walk through this and do the math, we get meters times seconds over seconds equals meters. Seconds cancel. You can see that. What we're left with is meters equals meters. Is that a true statement? Yes. Therefore, this checks out dimensionally. our rearrangement checks out dimensionally. Now, in three-part algebra, for most of you guys, this is ridiculous. But we're going to practice it with some three-part algebra, because then I'm going to give it to you with like six-part algebra. That'll be fun. Let's solve for time. Now, a bunch of sophisticated math using primates such as yourself should have no problem with this. However, I can tell you that sophomore physical science students or freshman physical science students, this is like a train running at a brick wall. It's been a long time. So I'm just going to go ahead and do the rearrangement. I'm not going to show any of my work. I'm going to say delta t equals delta x v, because that's what they usually give me. So I'm going to do the same process of dimensional analysis that I just did. I'm going to put my units in place of my variables. So time would be in seconds, displacement in meters, velocity in meters per second. And I'm going to go ahead and I'm going to do the math. I'm going to do the algebra. So that says seconds equals meters times meters over seconds. If I continue this to its logical conclusion, seconds equals meters squared over seconds. Is that true? No. So this is where we would put a does not equal. That slash through the equal sign means does not equal. And we would write not valid. So here I guess I should have written valid. That is not a valid expression. I have done something wrong in my rearrangement. My unit should get down to the point where my final step is a very simple statement of truth. Let's do another one. Okay, so we've done another rearrangement. We're going to go ahead and substitute this. I screw these up unless I remind myself that it's invert and multiply. So I'm going to do that step. Seconds equals meters times seconds over meters. Oh, this is looking more hopeful already. Seconds equals meters times seconds over meters. Guess what? Meters cancel. What am I left with? So I'm left with seconds equals seconds, valid expression. I know that the dimensional analysis checks out. Doesn't mean that I have the right equation. You can make up an incorrect equation for which the dimensional analysis checks out. However, if the dimensional analysis doesn't check out, you know you're wrong. So let's do a more complicated one. This is an old favorite for no logical reason whatsoever. This is one of my favorite of the kinematics equations. I don't know why. So if we want to solve for acceleration, let me do a little bit of magic and do a rearrangement. I have the square root of 2 times quantity delta x minus vi delta t divided by delta t equals a. And I'm pretty sure plenty of you are already aware of whether or not the algebra on that one was good. But let's go ahead and plug in our units. The other thing that's going to happen is any numbers in the equation are just going to disappear because we don't care about them. We're not worried about the numbers. So I'll switch colors. We get rid of the 2. We have the square root of meters minus, well, velocity would be in meters per second. Time would be in seconds, times seconds, divided by seconds, equals, acceleration we haven't talked about a lot yet, but acceleration is typically given in meters per second squared. So we'll start with getting things under the radical cleaned up a little bit. Okay, so I've got meters minus meters times second over seconds. My seconds will cancel. I have meters minus meters over seconds, square root thereof. Whoops, I put an A in there. I can't believe I did that. Nobody yelled at me either. Okay. Meters minus meters over seconds, square root thereof equals meters over seconds. If I subtract some number of meters from some other number of meters, what are my units on that answer? Meters. 10 meters minus 6 meters. My answer is 4 meters. So don't think, oh, well, meters minus meters, it's 0. It's not 0. We're talking about the units here, not the numbers. So that simplifies down to meters over seconds equals meters over seconds squared. Is this a valid expression? No. We can't take the square root of meters over seconds. If it was meters squared over seconds squared, we could, but right here we're stuck, and this is not true, so we would say not valid. Take your 4 minutes. Okay, so we've got this expression. This is another commonly used kinematics equation. Final velocity squared equals initial velocity squared plus 2a delta x. So if we want to solve for the initial velocity of the object, what do we have to do? So I've got an expression. I'm in the middle of a test or something, and I'm all stressed out, and I'm feverish, and I can't breathe. Oh, no, that's just right now. And I think I solved this right. Did I solve it right? I don't know. So let's do the dimensional analysis and see. Same steps as ever, as always. And the first one is just getting rid of any actual digits in the problem because we don't care. And we're going to go ahead and put in our units. Velocity would be in meters per second. This is, of course, squared. So we've got meters per second, quantity squared. Minus, well, acceleration is in meters per second squared. And displacement is in meters. We're claiming that this is all equal to a velocity, which would be in meters per second. So let's go ahead and start on the algebra. I've gone ahead and distributed that exponent, so I have meters squared over seconds squared. I'm going to go ahead and multiply my meters per second squared times meters, which gets me, hey, meters times meters over seconds squared. And I'm claiming that this is all equal to meters per second. So I have the square root of meters squared over seconds squared minus meters squared over seconds squared. Once again, I'm going to shrink and move that. So if I subtract meters squared over seconds squared from meters squared over seconds squared, what are my units? Meters squared over seconds squared. Okay, so the square root of meters squared over seconds squared, I'm claiming equals meters per second. This is looking pretty good so far. If I take the square root of meters squared over, square root of meters squared over seconds squared, what do I get? Well, I get meters per second equals meters per second. This expression is valid. Okay? So that is what I would write. You good to cut loose? Questions? The F. Oh, it doesn't matter. It doesn't matter. Because we're just saying, those are just our initial variables in the problem. That was a final velocity. All we care about when we're doing dimensional analysis is the units. Okay. That's a good question. It's the same reason we can get rid of the 2 or a half or anything else like that, because we're only concerned with the units in dimensional analysis and seeing if the units check out. Making sure that our units cancel and that we can do algebra. And you're always thinking about, you know, if I had a coefficient of 1 in front of this unit, what would my units be on my answer? Okay? I'm going to cut you loose to do the practice problems. Okay, so work on these problems on your own. While you're doing that, I'm going to find and print the extra dimensional analysis practice sheet because you will have a 5th quiz tomorrow on dimensional analysis where I'll give you probably 8 dimensional analysis problems, and I'm also going to throw some more conversions back at you because I feel like you need that based on results.